Okay, the first thing we're talking about today, there will be passive filter. Basically, we get two different types of the filter. Passive filter and active filter. When you learn electronics, you will be learning about active filter. Okay? What the difference? In the passive filter, they're using only RCL. We don't need any power. And the active filter, they're using the amplifier. Okay? Amplifier, that means they need the power supply. That is the difference. The way working will be the same. Okay? Today we're talking about passive filter. The filter are circuits that are capable of passing signal with a certain selected frequency, while rejecting signal with other frequencies. This property is called selectivity. That means they're using the filter to select a certain frequency they want to see it, okay, and block any frequency we don't want. Passive filter URCRL or RCL circuit. The passive circuit provides frequency selectivity. The four basic categories of passive filter are low pass filter, high pass filter, band pass filter, okay, and band stop filter. That means that on the filter you get low pass, high pass, band pass, and band stop or notch filter. First thing we're talking about, low pass filter. If you're looking on the circuitry, very simple. The circuitry only get resistor and the capacitor. This is V in and this will be V out. See, that's very, very simple. First thing we're talking about one pole low pass filter. Okay, now you get a 1 pole, 2 poles, 3 poles, and so on. In order to know that a 1 pole, you get only 1 resistor and 1 capacitor. Exactly that what you can see here. 1 resistor and 1 capacitor, 1 pole. Low pass filter only allow low frequency signal from 0 Hz to its cut-off frequency FC, going to path wide, blocking not any higher frequency. Okay, they're talking about the cut-off frequency. Last time I already telling you. Cut-off frequency can be a critical frequency. When we stop frequency, corner frequency, That means at that frequency, output will be going down minus 3 dB or equivalent to 0.707. Okay? For the cutoff frequency or corner frequency, critical frequency, they calculate by the formula here. FC equal 1 over 2 pi RC, where F will be in Hertz, R will be in Ohm, C will be in Farad. At the cutoff frequency, the gain is down minus 3 dB, or the output going down to 70.7%, okay, of maximum value, equivalent to 0.707. After cutoff frequency, output decrease. At a constant rate, at the frequency increase, okay? That is when the frequency is increased tenfold, 1 decade. The voltage gain is divided by 10. In other words, the gain decreased 20 dB each time the frequency is increased by 10. And now we're talking about one-pole low-pass filter, 1R, 1C. Roll-off rate will be 20 dB per decade, equivalent 0.1. Two-pole, that means you get 2R, 2C. Roll-off rate will be minus 40 dB per decade, equivalent 0.01. And the next will be 3 poles, 3R, 3C. The roll-off rate will be minus 60 dB per decade, or 0.001. Okay, this is the gain, okay? And this is the frequency domain range. That means they vary with the frequency. So the bandwidth of the signal for low-pass filter from 0 up to cutoff frequency. Okay. After that, after the cutoff, we don't care. This is the ideal output. And this will be a practical. Okay. We cannot get the ideal. Normally, we're working with the practical filter. Now, this is the mid-range. My question is, what is the gain in here? You know the gain AV equal V out. I want to know, this what we call a mid-range. What is the gain of the mid-range? Equal what? You know, this is again, they're using the dB. So who knows what is the gain at the mid-range equal? Just nobody know, Mr. Smith.
The gain's going to be 0, isn't it?
Now, that is, you say they say 0 dB.
Oh, oops.
Okay, if I'm looking in here, I can say minus 3 dB equivalent to 0.707. They're telling you if you want to take a log, they can be 20. Log of, let's see, 0.707. What you get? You take the log of 0.707. What you get? Take 20 log 0.707.
-3.
Minus 3 dB. That means you want to know what the really a number equivalent minus 3 dB. You take the log of 0.707. And now you want to say what equivalent to 0 dB. If you take the log, okay, let's see, 0 dB, okay, that means of what? See what you get.
The log of 1 is 0, correct?
Log of 1 is 0.
Right, and 0 times 20 is 0.
Okay. However,
But you asked what is the gain of the mid-range?
Basically, the gain of the mid-range is supposed to be 1. Let's see. That's telling you 0 dB equal to 1. So that's telling you in here, the gain equal to 1. Okay? That means output, input will be the same, no loss. Okay? And the cut off this point here. They said the output going down 3 dB. Okay? So that will be telling you they down 0.707 times the input. I given you example. VE volt at mid-range. V out equal 10 volt. That means whatever coming in will be coming out, no loss. However, at the minus 3 dB, at this point here, V out equal 0.707 times 10. That will be telling you V out equal 707 volt. Again, I already telling you, you cannot do anything with the decibel. In order to know, you have to convert it into the numerical. Normally, you're working in the RF radio frequency, and they will be measured to get the dB or dBm. However, we have to deal with the watt, milliwatt, kilowatt. Okay? Then that's why you have to know how to convert it. The following show the response for RC low pass filter with the different poles. Now, if you're looking on that one, the first one right here, they will be minus 60 dB per decade. Okay? And the second one will be minus 40 dB per decade, 2 pole. And the last one, minus 20 dB per decade, 1 pole. So when you're looking in the output, okay, then you can see which one will be better. First thing is we want 60 dB. How come? The thing is we want to, after the cutoff, they will be get the, reduce the output quickly. That take a little longer. This one is not good, okay? When you tune in your radio, when you hit into the point you want it, you don't want the noise. So that's why the filter will be cut it off as soon as we can. More dB per decade. That will be much better. Okay. Cutoff frequency, we already gave it to you. This is the formula. Okay. And if you want to calculate the cutoff at any time, any frequency, you can using this formula. Okay. V out will be equal to HC divide square root R square plus HC square times VE. Okay. So shown for cutoff frequency, FC for the following low pass filter. You get R here, you get 2 nanofarad. You apply to this formula. Okay. And the answer will be 7.96 kilohertz. You can see that very simple. Normally, in the final test, most of the questions will be not try to do much about calculation, just asking about how much you understand. Now you get RC, high pass filter. That is the thing when you're looking into the high pass, low pass filter, you need to recognize which one is a high pass or which one will be a low pass. You can see the difference. On the low pass, capacitor here. And the high pass capacitor here. That is the high pass. And the formula calculate cutoff frequency will be the same. Okay. And they will be pass any signal higher than the cutoff. So you get the first one, low pass filter. They will be pass any signal lower than the cutoff frequency. And high pass, they pass any signal higher than cutoff frequency. This is the RL, low pass filter. That means they're using inductor and resistor. RL low pass filter, cutoff FC equal R divided to 2 pi F. Same thing, pass any signal lower the cutoff frequency. Output at any frequency. Okay, you can calculate using this formula, and they gave it to you shown for cutoff frequency FC. You apply to this formula. You're able to calculate to get the cutoff frequency. The answer will be 3.183 kilohertz. Okay, but I want to make sure you understand when you're looking into the passive filter, you recognize is it a low pass filter or the high pass filter? Using either RC or RL. And what is the low pass filter? They will pass any signal less than the cutoff frequency. And the high pass filter, they will be pass any signal higher than the cutoff. That is the difference. The circuit, they can be different either using inductor and resistor, or they can using capacitor and resistor. Okay, that's what you need to recognize, try to understand. Now we're talking about RC high pass filter. Okay, you get the signal here. Okay, I'm looking into the circuitry. I know this is a high pass, and that will be, you can calculate the high pass filter by this formula here. FC 1 over 2 pi RC. And this will be a display the output, okay, for the high pass filter. This point here will be the cutoff frequency. How do we know? The thing is they will be down minus 3 dB. So when you're looking into that, and you can see this look like the gain equal to 1. Okay, that means you get no loss. So that's why any signal with the frequency higher than FC, they will be passed. That's what we call bandwidth equal bandwidth or pass band. Any signal they can pass if the frequency higher than cutoff. And this just given to you the high pass for RL circuit.
Hey, Mr. Pham,
Yeah.
can you go back to that where you just left? Yeah. So for those two circuits right there, say like the first one where it says RC, when you got the capacitor on top and the resistor on the side, that's high pass. But if the resistor's on the top and the capacitor's on the side, then it's low pass.
That will be.
And then, I'm sorry?
Just a minute. Let's see. That's RL low pass filter, right? L
Right.
here.
Yeah, I guess basically.
Okay, I know. This is wrong. This is right? No. This is L here. Low pass.
Right.
R here.
Right.
And now this is high pass, they opposite.
Right.
This
And it's the
R,
same.
this
So,
L.
so for R and C, based on where the resistor and the capacitor is, that tells you whether if it's high pass or low pass.
Right.
Okay, thank you.
Yeah, the thing is that's what you try to get along with the circuit. You're looking into that, you know, high pass or low pass. And most of the circuitry will be using RC, not RL. Bypass capacitor. This is what they call a bypass. Now, capacitors are connected in parallel with a resistance for the purpose of bypassing or something AC signal around the resistance above a specified frequency. The above circuit shows a bypass C1 connect across, okay, to bypass R2 effectively, okay. HC value must be 1/10 of the value of R2. The result is practically zero AC voltage across R2. The frequency that produce HC value 1 kilo ohm or less, the circuit is defined a low pass filter. That means this one try to get the signal pass through that one, okay? So that's why you still get R1 and C1 is the low pass filter. In order to make sure you get they will bypass, okay? That means they're telling you right here. HC value 1 kilo ohm or less, okay? That means when you calculate the HC, so they have to be 1 kilo ohm or less of the joule. However, that's nothing to do for the technician. That's for the design, for engineer, okay? When they design the circuitry, they need to know. We are testing, okay? So you cannot do anything with the circuitry. Only make sure you can get whatever engineer want to get.
Would that circuit be a low pass?
This one will be a low pass
Right.
without R2, right?
Yeah, without R2.
Now, talking about band pass. Okay, so don't worry about that circuitry. Cannot memorize. Even myself. However, everything they will be telling you in the document, okay? This circuitry will be band pass filter, okay? Only thing is you need to know what happened for band pass filter. Okay, band pass filter. Response. Pass frequency higher than FL and less than F high. So basically, on this output display here, you can see they get to cut off frequency. One will be this point. That's what we call F low. And one will be on the other side. We call F high. So the band pass filter will be pass any signal higher than F low, less than F high. Okay. Bandwidth that means you measure from F low to F high equal F high minus F low. Okay. And you get the frequency here, they call a center frequency. They will be square root of F1 times F2. Okay. I think that will be a F low times F high. And also you get the quality Q. Quality Q, that means how good the filter will do. Equal, you take the F center divide to bandwidth. You get the quality Q. Quality Q control the zone of rate and the bandwidth of the filter. Okay. So when you're looking into the response, and you know this is the output of the band pass filter. They only pass the signal higher than the first cutoff and lower than a second cutoff that they call a band pass. Okay. And if you want to calculate the bandwidth, this is the formula. You take F high minus F low. You get the bandwidth. Okay. And if you want to calculate the quality of the filter using the formula, you take the F center divide to the bandwidth. And the last one, band stop, not filter. You can see this is a circuit. However, if you're looking at the output here, you can see you also get to cut off one FL and another will be F high. This will be opposite, okay, to the band pass filter. They allow any signal higher than F high or less than F low to pass, okay? And they will be reduce the frequency higher than F low or less than F high. So basically, this just the opposite to the band pass filter. Normally, you interview, if they asking you, they're not asking this circuitry. They're asking about that one. They can ask you if you're looking into the display, telling me what is it. So the answer will be, that will be the output of the band stop filter or not filter. Okay. The circuitry, most of the people, even normally engineer, they couldn't remember. Okay. They just
That's a
want to
tank
know.
circuit, right?
Yeah. They just want to know when you're looking into the output, you know that is the output of band pass filter or band stop filter or low pass filter or high pass filter.
Hey, Mr. Pham, did
Yeah.
Did that, where it says FC, the cutoff frequency, does that go all the way down to that line?
Yeah, that will be the center frequency.
So it goes all the way to the very bottom.
Now that's going down here. Okay, they're not telling exactly the value, but they say that for decibel.
I understand that, but my question is it all the way to the bottom?
Right.
So
You
what
can-
value is it if it's all the way to the bottom?
Exactly.
No, I'm asking you, what value is it?
Now, they going down here. They're talking about a frequency.
Okay,
They're talking about a frequency. That means when you apply to the circuitry, depending on what the frequency signal will be go. Okay? And they will be telling you what the cutoff center frequency with that signal. In here, in general, they're not talking about specific frequency. So that's hard to say.
okay.
You can see the cascading filter section, narrow the bandwidth and improve selectivity. You can see in here, there can be a low pass, different type. Second one here, night, and so on. Now, the first one, 4 section, 4 pole. The next one, 3, 2, 1. So basically, V1 that one. Why V1 that one? That will be telling you the bandwidth will be small, right? Smaller than the second one or the next one. So when the narrow bandwidth, that's for the good selectivity, and that will be less of noise, okay? Before, maybe 15, 20 years ago, when you're tuning your radio, moving from one station to another one, you can hear a lot of noise, okay? Now, they can get a much better. When you're moving, you didn't hear anything until you get into the station you want. I've given you the example. You're tuning radio AM, 760 AM, okay? Then you can get into the station you want with less of noise. And this also shows you, in general, a different filter designed by different engineers. The first one, temperature. The next one, electrical. But the worst and best cell. Different engineer design different filter. And this one here, what is it?
Noise.
The noise, exactly. The noise, that means the signal you don't want it. Okay? So if you compare between the different filter, best cell, but the worst electrical temperature, which one do you think is the good one?
The two best ones is Bessel and Butterworth, and I think Bessel is probably better.
Okay. The first one, Jeopardy here, they get noise. So we don't want. We don't want noise. Okay. The next one, elliptical. Also more noise, right?
Right.
So you don't want. Bessel and Butterworth, they have a no noise. Okay. However, between Bessel and Butterworth, which one you think will be better?
Bessel, because it's got a better dB response.
Bessel will be much better. The thing is, the cut off quickly, right?
Right.
That takes a longer time. So that's why you can get a noise. So basically, filter have a not much state. Okay, what I expect you when you're talking about low pass, then you have to understand what is a low pass filter. Pass any signal less than the cutoff frequency. Okay. High pass filter will be pass any signal with the frequency higher than cutoff. Band pass filter, they will be pass any signal with a frequency higher than the low cutoff and less than higher cutoff. And stop frequency or notch filter. Pass signal less than the lower cutoff or higher the cutoff. They basically just opposite to the band pass filter. Okay. Okay, so now we just go through quickly for transformer. Okay, let's see what they're saying here. Suppose two inductor are placed in close proximity to one another, but no electrical connection exists between them. Okay, so basically, this will be from the left volt. Okay. Suppose also that an AC voltage is applied to one of the inductors as so. The magnetic field surrounding the inductor with the applied voltage L1. Okay, applied voltage here. Induce a voltage into the other inductor L2. This phenomenon is known as mutual inductance. Inductor coils arranged in this manner result in a common electrical device we'll call a transformer. Okay. The coil are widened with the applied voltage in the primary. That means this side will be a primary. This side will be secondary. Okay. The coil that develop voltage from the magnetic field is secondary. If you see here, it's a primary, and this will be a secondary. The amount of voltage induced in the secondary depends on the ratio of turn of Y between two windings. Okay, in the figure, which coil are winding is primary. That's easy. If you see where you apply the voltage, that's the primary. So that will be the primary, L2. And L1 will be secondary. Okay, and this they just given you the different type of the transformer. Above are various transformer schematic symbols. The presence or absence of line between the coil indicate the type of core used. Iron coil, ferrite coil, air coil. This figure shows an iron core transformer with a tape secondary. This tape may be used to alter turn ratio between the two coils. Okay, that will be a center tape transformer. The turn ratio of a transformer is the ratio between the number of turns of Y on the primary. Like this one will be 10 turns, and this one will be 1. Okay. NP, primary turn, and the number of turns of Y a secondary, and H, that means secondary turn. On that one here, you can get NP, they given you 1,000 turns, and that will be 100 turns. A transformer with 1,000 turns on the primary and 100 turns on the secondary has a turn ratio 10:1. That means you take the 1,000 divide 100, so you get 10:1 ratio. Okay. The ratio between the voltage on primary, what we call VP primary, and the secondary VF equals the turn ratio of the transformer. NP over NF equals VP over VF. So that one they just using okay. NP over NF equals VP over VF equals 10 divide 1. A transformer having a secondary voltage that is less than primary voltage, that's what we call a step down transformer. That means when you apply 90 volts and the output on the other side only 30 volts, that's what we call a step down from 90 volts down to 30 volts. However, if you get a VP 90 volt, VF 100 volts, that's what they call a step up transformer. Okay? That will be a step up transformer. The tap of a center tap winding divided the number of turns in half. A transformer with 1,000 turns primary, lit 1 to 2, and a 500 turn secondary 3 to 4. Normally has a turn ratio 2 to 1. That means 1,000 divide 100. Okay. However, if the secondary has the center tap, the number of turns from the tap to one end, lit 3 to 5. Okay. Or lit 4 to 5 of a secondary is 250 turns, resulting in the turn ratio 4 to 1. That means 1,000 here, okay, basically from 3 to 5, 500. And now if they get a tap right here, they divide another half. So that's why you get 250. Okay, so basically that will be the same when you guys doing the level in a transformer. Then you can, read again the current ratio between primary and the secondary. Current ratio means IF over IP. I of secondary divide I of primary. Okay. The current ratio is the inverse of the voltage and turn ratio. That is, if the voltage ratio increase, then the current ratio decrease. If the voltage ratio decrease, the turn current will be increased. The thing is they will be opposite. A transformer with a voltage and turn ratio 10:1 at a secondary current 100 milliamps. What is the primary IP current? That means you can substitute into that formula and you can calculate it. Now you get a load right here on the secondary. If the load IL across the secondary of the transformer, then IL decrease or increase in the resistance, the transformer automatically increase or decrease the primary current. This characteristic of automatic compensation is why transformer is a self-regulating device. That means you changing that one, then the current will be changing. The power in the primary, P primary equal IP times VAC equal the power in the secondary, PF equal IF times VIL in the ideal transformer. We cannot get the ideal anyway. In the practical transformer, however, the primary power in, can equal the secondary power out only when the transformer is 100% efficient, which only occur in the ideal. After you measure the primary and the secondary power, you can calculate the efficiency of the transformer from the following equations. Efficiency percentage equal take the P of secondary divide primary times 100%. Okay, an ideal step down transformer with the voltage ratio 10:1 at input power 500 milliwatt. What is the power of a second? Okay, so you can using that one formula to calculate it. Last one, the transformer is for impedance matching. Now, you see the first one, generator here, 10 volt IMF. That is the internal resistance of the generator, 50 ohms. This is the load you connect into that. For this circuitry, okay, they calculate, they get the power of the load equal 444.4 milliwatt. In order to do it, they're using the formula here. V short divide Ri plus R square times RL. Okay? And anyway, they calculate they get 444.4. Now, on the second one, the difference is what? They change the load to 50 ohm. Okay? And they do the same calculations. They get the power out 500 milliwatt. Okay? The last one, they change the load to 75 ohms. And they calculate the power. They get the output power 480 milliwatt. Okay, so basically they're telling you what going on. On the load 25 ohms, they less than 50 ohms. That's what you get for 4.4. And now on the last one, you get 75 ohms. That's higher than 50 ohms. You get 480 milliwatt. And on that one, they get 50 ohm, 50 ohm. You get 500 milliwatt. That only telling you one thing. The impedance have to be matching 50 ohm here, and that have to be 50 ohms in order to get the maximum power. Okay? Input resistance, output resistance at the same value, then you get the maximum power. Okay, let's see. The last one, reflect impedance. A transformer can make a load RL. That means the load right here. Resistance appear to primary at a value larger or smaller than its actual resistance value. Okay. Suppose it is necessary to transfer 500 milliwatts of power to 4 ohms. That means they transfer from generator here to the load 4 ohms. To transfer maximum power from generator to the load IL must somehow to be transformed to a value equal 50 ohms. This is, we can use transformer to step up the 4 ohm load in the secondary to 50 ohm in the primary. That's what they want, is try to bring it up. That one, same thing, 50 ohm. That way you can make the impedance matching. The impedance reflects back into the primary of the transformer using the following equations. Gp equal Np over Ns squared times Gs. That's the secondary impedance. Now, for the circuit sold. GP equal 3.53 divide 1 square times 4. That will be 50 ohm. Okay. And PL power load, power output, V square ohm divide to RL. Okay. That means you get, let's say, 1.414 square. Okay, divide 4. You get a 500 milliwatt. Let's see. Okay, what they want to do. Okay, they want to select the ratio between NP and NS. Okay, so this is a generator. Okay, and basically you can see if they try to get the ratio 3.53 to 1, okay, first thing you can get a GP, that means impedance, okay, of the primary, and you get a 50 impedance, and this is a 50, so the voltage now will be voltage divider, and you get a 5 volt AC, okay, and the 5 volt AC here, if you get a ratio 3.53 to 1, that's what you get. VS now will be 1.414, okay, and that will be given you maximum the power here. See, GP equal 3.53 divided 1 square. That means they want to calculate impedance at this point, and you get a 50 ohm. So 50, that's why you get 5 volt. And the PL, that means the power at the load. You take the V square divide to RL. V square, that means the secondary here, square divide to 4. That you can get maximum. Okay, so basically that is nothing to do with the guy. Okay, that basically for engineering when they design the circuit. Okay. Example for circuit cell, calculate primary impedance, GP. So it's given to you, GP equal NP over NS square times RL. Okay, NP is 5, NS is 1, RL will be 8 ohm. Okay, and then they say to find the turn ratio, NP divide NS, when the impedance ratio is known. NP divide NS equals square root of GP divide GS. Let's see what they say here. If it desired to transform 8 ohm resisting load in the secondary to 1 kilo ohm in the primary, calculate the required turn ratio NP over NS. So basically, if you want to understand more, you have to go through again. Okay. That means they want to calculate the GP here. And we already know from that one. GP, okay? NP divided NS square times GS, secondary impedance. So GP equal primary divided secondary square times 4. Then you can get whatever voltage, okay, on this side, okay. Then you can get the voltage here. You can using V squared divided IL, okay. That will give you the power. So not much thing will be in the transformer, okay? And if you get anything you want to know, just let me know. And also on the 17th, we get the final test. I don't care how long you stay in the program. You have to get through the test, okay? The test will be running. If you turn in after we complete for the report, you can get maximum will be A. However, after 1 day, you turn it in, the maximum you get will be B, okay? In order to pass, you have to get at least C. We get the total will be 50 questions. 8 questions with 2 points. Okay. Most of the questions will be regarding to your understanding. I'm not giving you much of any calculation. And next week meeting, August 10, I will be talking about IF. That means try to let you understand how the signal transfer over the air. That means the signal going out from the radio stations. And they will be coming in to your radio. Basically, we're talking about 2 things. One will be transmitter, signal transmitted over the air. And the next one will be talking about receiving, when the signal go into your radio. Okay, what will be happen until they can go to the speaker. So we get 2 days for the IF. 1 day will be August 10. A second day will be August 24. We have nothing to do with the IF. No test on that. Just for you guys understand, okay, the application of the signal transmitter or receiver in the radio. Okay, so any question, anything? Try to get your AC1, AC2, left volt, done as much as you can. Okay. If I get a chance on the class, you get any questions, let me know. Any question also including the assignment, I will be help you out. Okay. Okay, so any more questions? Anything else? Okay, so if it's not, good night, everyone.
Good night,
Thank
sir.
you.
Okay, we'll see you on Tuesday. Okay, bye-bye.
Goodbye.